Video unmute. Okay, there we go.
Can you see me?
We can't see you, but we can hear
Got
you.
video sound. Okay, there we are.
We can see you.
Yeah, we can see you.
All right, how's it going?
Yeah, good.
Pretty good, I think. The report's up to having the sphere with 4 vertices.
You can share him.
Oh yeah, we can share it too.
Okay.
We paste the link from
Do we share that? Oh,
It's got unlimited collaboration.
Ooh.
Can just try it.
Sometimes switch control on FM, so I need to. Alright.
I don't know this one.
What?
Cool. 2 dots. You said that's a lot for 3 dots.
What?
You said there's a lot for 3 dots.
Yeah, there's a lot. Like, actually a lot. You can't. Because, yeah. Like, you have the cube, you have the dodecahedron, you just have any arbitrary prism, have trees, and then, like,
Oh, I forgot to add the cube.
yeah, you have dodeca? Yeah. Well, cube falls under prism, so it should be fine.
Then add the prism.
Any arbitrary prism should work.
Yeah.
Well, this looks for just 1 line, 1 dot. Or it was 1 line, 1 dot.
Oh, yeah, it's like the early one.
Oh wait, oh yeah, yeah, so the triangle prism.
What about 4 is weird.
4 is a lot. Like, no, like it has a lot of cases. Compared to the first 3. It has more than the first 3 in total. Interesting. Like 10 cases or something. Triangle only has 4. Right. But we know the square leads to octahedron, right? That's a clarification.
Yeah, it's good.
This one leads to something, but
What is
the line.
Oh, yeah. You have to ask him.
Yeah, but I forgot. Oh, I don't know. Triangle point, I've investigated. 2 lines, haven't investigated.
You have like a triangle and it's thick one, yeah.
What are you working through now?
We shared with you the doc. It's a link in the chat.
Oh, okay. Sorry, I thought you were going to share the screen.
Oh yeah, my bad.
I was just
Oh,
waiting
you
for
can
something
do
to
that
happen.
if you want. Do that if you want.
Okay, now I've got the document right.
So we'll go with this something went wrong. And we'll go to vertex transitive graph. Wait, where's Zoom? Did it just disappear? Wait,
I'll tap.
Yeah,
What's up?
because I'm looking at the document now, you can't see me on Zoom. Can you hear me?
Yeah, we
Yeah.
can't see you right now.
wait, sure. It's working?
Or screen sharing if you.
Yeah. Does this work?
Let me go back to Zoom.
Yeah, that's right.
Click on rich text. Oh,
Yeah. Okay, I can see that now.
Right, no, Shucks, I think it's. Oh wait. Wait, what? How do you make it show both?
You want to compile it. That'll make it show, I think. Where's the button to compile? Oh, no, it's just messages, isn't it?
Yeah,
I don't know what this is.
yeah. Wait.
Just a minute. Yeah, is there a button on the right somewhere that says recompile?
There is on the other laptop.
Yeah,
messages. You want to, yeah. Can you get rid of the messages?
Let's close it something.
wait, how do you close messages?
Let me try. Alright.
That's the screen.
Recompile.
There we are. That's it.
Let's make that bigger. Can you kill messages?
What technique allows for message destruction? Menu. I don't think it's here.
Just full screen back.
Those guys. Yeah.
All right, good. So one vertex, two vertices.
Yeah. Two vertices.
Yeah. Hang on. So three vertices.
Yeah.
What am I? Okay. Can you just scroll back up a bit? Three
Yeah.
vertices. So let me just. Okay. Now three vertices. You start with a complete graph, then you get the tetrahedron.
Yeah.
Yeah.
Right, and then if you start with, let's see, you've got three vertices and
Two edges.
one edge.
Yeah, one edge.
Right, you get that. Okay, I think that's right. Yeah, then no edges. You get the tree.
Yeah,
and
you
many
got a
other
lot of stuff.
things as well. Yeah,
Yeah.
and then four vertices.
Yeah, we don't have that one since it's pretty trivial. Like, I'm pretty sure that's just the case of most completes. I think that's what all completes turn out.
Sorry, what was that?
The complete graph always.
Yeah.
Yeah,
complete
right.
graph.
If you start with the complete graph on four vertices, then you get the complete graph on five vertices.
Yeah,
Yeah.
and it'll work.
Yeah.
Right. Okay. Good. And you got some nice pictures there. So how are you drawing these pictures?
So for some of them, like the tree, we use your thingy.
Yeah.
Most of
So
them
I
we just
can-
looked up online.
Right. Okay. You could use a drawing tool and then export a PDF and include that. That's one way to go if you can't find things online. So you're up to 4 vertices anyway.
Yeah.
Yeah.
So how many different graphs are there in this case?
There's like a lot of cases, like at least 1, 2, 5. Because I got like a lot of stuff with it's like 3, 4, 5 edges.
Which one?
How many spheres are
What?
there? 4.
Or 4?
I think that website we were looking at yesterday lists them all. Tells you the number.
Can you send a link again? Do you have it?
Oh, I can find it.
I think I got how many is this?
20 something.
Is it right? I got 10, but that's because I try to build on like repetitions, like with rotations, and just like.
Oh no, the other website it counted by vertices of the like the entire thing. Yeah, it wasn't by vertices of the sphere. I'm pretty sure.
Sorry, what was that again?
Like it sorted the graphs by vertices of the entire vertex transitive graph, not just the sphere. I'm pretty sure.
I didn't pick up that there's background noise there. You sorted the graphs by what?
The website yesterday sorted the graphs by like all the vertices, the number of vertices in the entire vertex transitive graph, not just the sphere.
Yeah, well, it wasn't vertex transitive graphs. I think it was all graphs, wasn't it?
I'm not sure.
Anyway, there are plenty of places to look up where you can see how many graphs there are with a given number of vertices. I'm just looking on.
Oh yeah, but we're doing it by like we're doing it by the number of vertices in each sphere, right? So it's kind of different.
Yeah, that's right. Yeah, that's right. By the way, you didn't. There's one for 3 vertices you didn't include. That's the line with 2 edges. That one doesn't extend. So I think what you've done is you've given extensions of all the ones that extend, but I don't think you've said that there's one that doesn't extend.
You mean? We've said that it doesn't extend. I think like the 2 edges.
Okay.
The 2
Right.
edges,
Okay.
Yeah.
Right. That's yeah. Right. Very short statement there.
Speaking of it, did you find out about the 3 edges one? The 4 vertices, 3 edges.
4
The 4
vertices.
path? Did you find out about the 4 path?
Well, the 3 path, 4 vertices, 3 edges. That one extends.
Oh yeah, 3 path, 3 path.
But
not
the 4 path, 5
4 path,
vertices.
4 path.
Yeah, 5 vertices and 4 edges. Yeah, I've asked around, and we don't seem to know the answer for that one.
Oh, okay.
Okay.
So if we can answer that one, that's good progress. Now, I was talking to another one of the research assistants working on this project earlier today, after I talked to you, and he showed me some work he's done where he's proved some results that about graphs that exclude the possibility that the graph can be a sphere in a vertex transitive graph. And he's tested this criterion. So, for example, he can show that about 46% of graphs with 9 vertices cannot be extended to a vertex transitive graph. It looks like from the trend is that that this criterion, there's be a smaller and smaller percentage as we increase the number of vertices. There'll be a smaller and smaller percentage of the graphs that are excluded by this criterion, but that, you know, that's only one criterion. That doesn't mean that that all the others do extend. So anyway, there is that work as well.
Oh, that's pretty interesting.
Yeah, so that's the sort of thing we can do. Try to come up with criteria that rule out on a graph that rule out it being a sphere in vertex transitive graph. And one thing he had was bipartite graphs. So do you know about bipartite graphs?
Yeah.
Yeah. So he was able to show that many bipartite graphs cannot extend, cannot be the sphere in a vertex transitive graph.
That's pretty interesting.
In fact, I think his criteria don't. And I asked him about the path of length 4 or the 5 vertices, and he thought that none of his criteria would rule that one out. That one is bipartite.
That's fair.
Maybe it was complete bipartite graphs. That's something to think about. If we have a complete bipartite graph, then can it be the no, but that would rule out a square, wouldn't it? A square or a 4 cycle is a complete bipartite graph. So maybe, yeah. Maybe it's only once the degree gets up to a certain size. I'll just write to him about that. He probably won't reply while we're meeting, but I'll find out.
Any good?
All right. Yeah, well, that looks like it's coming along pretty well. So we just need to work out the answer now for the other graphs with 4 vertices.
Yeah.
I think this can all be done. I remember doing it once, so I don't know that I still have the results. Oh no, oh no, sorry, you've got all 4 vertices, haven't you? Yeah.
Oh no, we haven't. We've only got.
Oh no, no, you're up to 4. Yeah, you've done 3. You're up.
Yeah,
to
we're
3.
up to 4. Yeah.
Yeah.
So for further 3 vertices with no that are not connected. Are there any other graphs that they can extend to?
Well, I think the if you go to the 3 points, so you've got the tree, and you've got a number of graphs there that other graphs that are not trees that it can be extended to. I think, in fact, there are many more than that. So you've got a cube, you've got a graph there. I think that's a dodecahedron, isn't it?
Yeah, that's the dodecahedron. Yeah.
Yeah. So that's one, but there are many others, I think. Is that true?
Are there like infinitely many others, or is it finite? Or
I think there could be infinitely many others. Yeah. But oh yeah. So take let's take one set of cube.
yeah.
Now you can make another one by, for each vertex, replacing each vertex with a little triangle. So replacing each vertex with 3 other vertices and joining them all up.
Well, wouldn't that make?
Can you see what I'm saying? So we now get 3 times as many vertices. We get 24 vertices. And we can move any vertex to any other one. It's not a regular polyhedron anymore, but it's still vertex transitive. Every vertex looks the same.
So once you make one of the, you replace, like, wouldn't that mean this thing is
You do this for every vertex.
disconnected though? This vertex is like, this one's connected.
This, this. What?
I don't know.
Like, how are you defining?
Just
Yeah. Oh boy. Yeah, it's a solution for this.
yeah, solution for that.
Yeah, it is.
Wouldn't that be a solution for like the 3 dots with 1 edge?
Sorry, what was that?
Sorry, wouldn't that be a solution for the 3 dots with 1 edge? Like this one?
Okay, right.
But yeah, we'll add that in after. Yeah,
Yeah.
that's pretty cool. Yeah. Wow.
And you see that works whenever you have, so it works for the tree as well. If you look at the tree, replace each vertex with a little triangle.
Right. But that would also, the sphere would still be a 3 dots with 1 edge, right?
Sorry, let's see.
That's how you. Yes, you can do the other tree. You can do the other.
You can probably do this.
Yeah, you can do it with like everything.
Yeah.
It's basically like cutting off the corners and
Yeah.
making them to.
Yeah.
they
Whenever
call
you
it
have
cutting.
a corners, 3 corners like that, you put in a little triangle and you get another one of those.
Right, so it's like cutting the corners of a prism or something.
Yeah.
Alright.
Or
And you can do it for the tetrahedron. You've got the tetrahedron there.
Infinite corner cutting.
Yeah.
So could you keep doing that then?
Yeah, you can.
So there will be infinite number of transitive graphs for the one with one edge.
Yeah.
So I'm just wondering about spheres with like no edges and 3 dots. Would there be more than these? What?
No edges and 3 dots. Yeah, I think so. I thought I attempted to answer it there, but as you point out, the answer wasn't correct.
Cut corners.
Cut corners. Cut corners equal broken. Like, I like how I could possibly visualize it. Like, you cut the edges of a cube until like slowly turns into a sphere. That would be pretty cool.
That would be pretty funny.
Yeah. Eventually, the sphere.
Get like a net of a sphere.
Yeah.
Let me think about that. I have an idea they're infinitely many, but I just can't remember them at the moment.
Okay, yeah. I'll think about that too because it's hard to like find lists of things that are larger than that have the golf graphs that have more than like 5 vertices because
Yeah,
there's a lot.
yeah, it starts to be hard to visualize them. I've got a couple of answers here. So Aditya wrote back and said that if you have a complete bipartite graph where the number of vertices in each part is different, then that cannot be a sphere, a one sphere in a vertex transitive graph.
Right, so that makes sense for like the 3 dots with 2 edges, right?
That's right. That's exactly that's the smallest example of that. And there'll be some other examples that we start to meet. And then there's a couple of answers about the line with 5 vertices.
Would a square qualify as a complete bipartite?
Square.
Yeah.
Yeah, that's it's not complete, is it?
No, it's not complete. Wait, no,
It's bipartite, but it's not complete.
Wait, what's it missing?
Yeah. No, that's just complete graph. I think that's bipartite.
Yeah.
I'm not sure what that one was, but we have to try it when we're doing the 4 vertices,
Yeah.
which will be kind of a thing.
That's true.
Yeah, what do you say about the 4 part or 5 part of it?
Yeah, there's so Marcus wrote back about the 5 vertices on the 4 path. And said we looked at it by hand, but we didn't get anywhere. He's also sent some information about drawing pictures. I might forward that to you.
Oh, okay, yeah, sure.
But then Brian Allspark, which is someone else who's working on this, he's written something, but I don't understand what he's written. I'm not sure exactly what he's referring to. He claims a 3 path doesn't work, but I sent him a picture showing it does.
Yeah.
So I don't quite understand his answer there. I'll have to get back to him about that.
Okay. 1, 2, 3, 4. Point.
I sent Michael the slides from my talk yesterday as well. But maybe you haven't got that yet. And I'll send him this information on drawing graphs as well, so he can give that to you. It's easier for me to email it than put anything in the chat. So
we can share with you our emails if you want to just email it directly to us instead of through Michael.
Yeah, okay. Although I'll send them now.
Oh, okay. Yeah, all right then.
Okay, so you want to talk some more about the 4 vertices, or you want to work those out yourself?
I think we can work those out ourselves. I think.
Yeah.
Yeah,
Okay.
it's just gonna take time.
It'll just be a bit long. Yeah.
Yeah, that's right. And I'll think about this a case of just 3 vertices with no edges.
Oh yeah, thank you. Yep.
Okay, shall we leave it there for now, and then perhaps meet again tomorrow?
Yeah, sure.
Yeah, sure.
10 o'clock tomorrow again?
Yep.
Just check. Yeah, that looks good for me. So I can see you then.
All right. Yeah. See you then.
See ya.
Right, okay.
Thank you.
See you.
Bye.
Bye. Yes. Okay.